How fast can you process SMF data from 1 billion CICS transactions? Hi, this is Andrew from Black Hill Software. Someone asked me whether Java has adequate performance for processing SMF data. So I thought I'd borrow the idea from the Java 1 billion row challenge and test how fast you can process SMF data from 1 billion CICS transactions using the EasySMF Java API. I'm going to read the CICS monitoring performance records and produce a report showing transaction count, average, minimum and maximum elapsed time, and average and total user CPU time grouped by Apple ID and transaction. The file containing the SMF data is 586 gigabytes. The records use CICS data compression, so they will need to be decompressed by EasySMF. The data hasn't been sorted or pre-processed for the report. I don't have enough DASD for 1 billion transactions on the mainframe, so I'm going to run it on a PC. The PC is an Intel i5-14400 with a 1TB Crucial P310 SSD. So it's a decent mid-range PC, but nothing extreme. Let's have a look at the program. I'm starting with the skeleton report from the EasySMF samples on GitHub. We don't need to do anything tricky or unusual in this program. The key to speed in this type of report is using a hash map to collect the data. We can use a Java record with the Apple ID and transaction name as the key and create a class for the transaction statistics. The add method accumulates the data from each monitoring performance record. We update the accumulated values and the minimum and maximum elapsed times. Now we can define the hash map to link the Apple ID and transaction to the data. CICS records need a dictionary to find the fields, so the first thing to do is read the dictionary records. I'll also keep some counters to report if we had any records without a dictionary. I'll specify type 110 subtype 1 records from the SMF record reader, then I can create the specialized SMF 110 record. I'll just change that variable name to avoid confusion with the Java record keyword. Now we can check that we have a dictionary, get the Apple ID and process each transaction. I'll get the transaction name, create the key, create a new transaction data entry if it doesn't already exist, and add the transaction. That's it for processing the records. Now I'll add the report. First, the headings. I need some averages from the transaction data, so I'll add those calculations to the class. I'll use Java streams to give me a sorted view of the transactions, then process each transaction and write the information. Then I'll call a method to write the report. Finally, I'll record the start time and report the total runtime. I'll just fix up these arguments to allow for the dictionary file and run it against a small file to check it's working. Looks good now for 1 billion transactions. Okay, we're back. That finished in 20 minutes and 17 seconds. It's certainly not instant, but not bad for a billion transactions. The program gives some information about the amount of data processed so we can get some statistics. We read 586 gigabytes in 1217 seconds, or 492 megabytes per second. We decompressed 420 megabytes per second and processed 3.1 terabytes of decompressed data at 2.6 gigabytes per second. How can we make it faster? Well, it's a single-threaded program on a PC with 10 cores and 16 threads, so the obvious answer is to split the work across multiple threads in parallel. This might not be a good idea on the mainframe where you need to share the CPU, but it's a good option on the PC. Java Streams allows you to specify parallel processing, so I'll change the program to use Java Streams and move the processing into a for each block processing each record. We don't really need this record count, so I'll get rid of it. If I add a parallel statement, the stream will run multiple threads in parallel. Then the processing in the for each block needs to be thread safe. Anything updated in the block needs to be protected from simultaneous updates by different threads. We can change the counters to use a long adder class. Java Streams actually provides functions to do the accumulation on each thread independently and merge the results, but I'm trying to make minimal changes from the original program for this test. I'll change the hash map to a concurrent hash map, which means that the compute if absent processing will be synchronized across threads when new entries are added. Finally, we'll make the add method synchronized. This synchronizes at the instance level, which means that the threads only have to wait if they try to update the same transaction entry. It's not global for the add method across the whole class. Now we can rerun the test with parallel processing in multiple threads. Okay, that finished in 7 minutes 18 seconds. That means we're reading a bit over 1.3 gigabytes per second, decompressing 1.1 gigabytes per second, and processing the 3.1 terabytes of compressed CICS data at 7.2 gigabytes per second. If you're interested in garbage collection time, Java reports about 7.9 seconds spent in garbage collection. We processed SMF data from 1 billion CICS transactions in less than 8 minutes. Hopefully that's fast enough to reassure people that yes, Java performance is good enough to process SMF data. This is 100% Java, so it'll run on the zip on the mainframe. I'll add the program to the EasySMF samples on GitHub and put a link in the description, so you can try it on your own data. If you need fast SMF reporting for CICS, why not contact us for a free trial? Tell me the reports you need and I'll add them to the samples. Thanks for watching.